Thank you for the nice introduction. Today I will like to discuss with our Russian friends about some recent progress in the study of kagome lattice. First, I would like to have some basic introduction, basic background on kagome lattice electrons, how we get there from the initial study of kagome mechanism, and then I'll focus probably more on my own our recent research in Southern University of Science and Technology. And lastly, I will give some outlooks in future opportunities, especially in study kagome spin liquid and related materials. So initially, in the 1940s, all the story begins around 1940s. And at that time, Onsberg has exact solution for the Ising model on the square lattice. And then researchers progressively study the Ising model on hexagonal lattice, honeycomb lattice, and then by the Japanese physicist Itoro Suyuzi to the kagome lattice. And here, kagome in Japanese word means bamboo basket, and mi means woven pattern. So it is this kind of pattern is actually widely seen in Asia folk culture. It's like this basket, and then I also did some archaeology in China during my first year back to China working here, and I tend to find that it is also from ancient China around 200 BC. So it's very ancient subject, a very ancient pattern. And recent few years, kagome lattice seems to become a hot topic. Here I referenced the Research France report from Clarivate in 2022, 23, and 24. You can see kagome lattice, kagome metals, or kagome superconductor research always ranked number 1 or number 2 of the top 10 research fronts in all disciplines of physics. This is based on their citation, visibility, and impact. So how researchers how we firstly see or firstly get a sense of kagome electrons. There's still it's actually a long journey from the initial study of magnetism. As I said, initially Suyuzi discussed the Ising model in kagome lattice, and then what he found peculiar is that if the interaction is if the spin interaction, exchange interaction is antiferromagnetic, then there is no solution for phase transition. So this has some similarity with the later on discovered quantum spin liquid phase. Means if the spin exchange interaction is antiferromagnetic, the kagome magnetization tend to be in a spin liquid phase. There would not be a long range magnetic order, and there could even be fractionalized spin excitations. And in the last century, there was also a big debate on the fundamental origin of magnetism. This debate is mainly initiated by Heisenberg and Stoner. In Heisenberg's view, the magnetism of the total magnetization is from spins localized at each atom, while Stoner views that differently. He thinks that it is actually from the electrons traveling around the crystals. So this big debates was initiated some interesting discussion of electronic structure driven magnetism. Yeah, at that time, in the 1990s, there was some flat band magnetism. It means if the system has some flat electronic bands, the system there could be an analytical model showing that the system can exhibit ferromagnetism. So in this background, uh, Michael and other physicists calculated the tight binding model for kagome lattice, and then they do found that there can be a flat band, and the flat band can introduce ferromagnetism. So through this journey, finally, the tight binding band structure of kagome lattice was unveiled. So it includes three essential parts, which were flat band, Van Hoff singularity, and Dirac cone. And then with this three band singularity, people started to focus some essential physics. One of the big topic was topological matter. This was probably initially suggested by Nagosa, where he considered a model consists of spins on the kagome lattice with different orientations. So the spin can have a spin Barry phase. The spin Barry phase work on the Dirac electrons will create a Dirac chain gap. So this chain gap was when we have the band filling just within the chain gap, the system will develop quantum anomalous Hall effect, very similar to the Howland model. However, such exotic spin structure or the Howland type of loop current order was very hard to visualize in real materials. Luckily, around 2005 and 6, people start to build up models for the topological insulator. So at that time, topological insulator was born. And then people realized that when we have spin orbital coupling, atomic spin orbital coupling, especially Kim-Lee type of spin orbital coupling, and then we further consider ferromagnetism, especially ferromagnetism along perpendicular to the kagome lattice. Then the system can also exhibit chain energy gap, and if the band filling is just within the chain energy gap, the system will exhibit quantum anomalous Hall effect, and there will be chiral edge states around the kagome lattice. And if the filling is slightly away from the chain energy gap, those system can still exhibit giant anomalous Hall effect, and this can be evaluated by the function of delta over ED. D is the Dirac cone energy. So if the chain energy gap and Dirac cone energy is comparable, the system can still have giant anomalous Hall effect. Another topic in parallel to the topological matter was many-body interactions. As said, the initial discovery of kagome tight binding model focused on its flat band magnetism. And if the system happens to have both spin orbital coupling, autoplane magnetism, and a fractional filling of the flat band, the system can also develop fractional quantum Hall effect, which has yet to be realized in real kagome materials. On the other hand, people also start to discuss many kinds of density wave orders. This is mainly because at the Van Hoff filling, the Fermi surface has some parallel features. So this leads to nesting People call this kind of parallel Fermi surface as nesting instability. So this nesting instability will drive the system either to a density wave order or to a superconductivity order. And um, lastly, people like Xiaogang Wen also start to discuss if we, because kagome spin liquid, well, at that time was a big shot, and if we stop kagome spin liquid, there can be exotic superconductivity, where in the model he mainly found time reversal symmetry breaking superconductivity. So on the material-wise side, initial focus was trying to looking for the Chen quantum phase or the quantum anomalous Hall effect. And initial effort was focused on this iron tin material. However, people start to realize that there are two problems in the iron tin type of material. One problem is that in the kagome lattice, there was always an additional tin atom in the center. So the ideal kagome type of electron hopping model probably was not suitable. And the other is for the realization of Chen quantum phase, we would expect to have C-axis magnetization. So the magnetization need to be perpendicular to the kagome plane. And the ground state of magnetic ground state of iron tin was within the plane. However, it have some other interesting pneumaticity order, and which was still on discussion. And then we try to find that this 166 material, terbium manganese tin 6, could be a candidate for realization of the Chen quantum phase. If we for this material, one benefit is that the large chemical potential, chemical pressure from the rare earth element will push the central tin atom out of the kagome lattice. So it has a purified kagome lattice. On the other hand, there are many kind of rare earth tunability, and for the special case was the turbine case. For the turbine case, the system magnetization was tuned exactly to the out of plane. So you can see it's a very good magnet. It exhibits a well-defined loop, magnetization loop for the C-axis magnetization. So these two things make it suitable candidates. And our STM image also reveals it's very large, and there were very large and clean kagome lattice. And if we apply a magnetic field on the kagome lattice, there will be a sequence of electron states generated. This is often regarded as Landau quantization. And on the termination that is not kagome lattice, we don't have this giant field induced Landau quantization. So the Landau quantization is a unique property of the kagome lattice in this material. Further, we can systematically apply magnetic field and see the Landau fan structure. This Landau fan structure can be fitted by mathematical form written here. So it has several ingredients. First is the direct energy, which can be determined around 130, and there are also Chen energy gap because we can see some Landau level gap, and then it also have a Dirac dispersion. If there was no this gap, then this become linear, so it's a Dirac dispersion, and we also have some G factor. That means this band is spin polarized. Otherwise, it will be split into two sets. The one set with large G factor means the system is spin polarized, so that meets with our standard requirement for the realization of the Chen energy gap. And we can invertly, with this parameter, direct energy, Chen energy gap, and velocity, we can draw band dispersion and compare with density with the density functional calculations, and it shows some consistency. And the most important to study topological matter is to build up some bulk boundary correspondence. In this case, as said, there would be chiral edge states within the challenge gap and on the kagome step edge. So in the STM, we can find kagome step edge and systematically study systematic image its states and different energies, and only at 130 millivolts, which was determined to be the Chen energy gap, and we detected robust edge states. And this we also study this quasi-particle interference and find within the Chen gap, the quasi-particle interference intensity was strongly suppressed. That was consistent with its chiral edge states nature. It means there will not be any backscattering. So that builds up a bulk boundary correspondence. And lastly, based on the semi-classical equation, we can evaluate based on our STM data, because we know delta, we know direct energy, so we can calculate the whole response, whole connectivity response would be 0.13 quantum Hall number. This was one order of magnitude smaller than the quantum anomalous Hall effect, but still regarded as the giant anomalous Hall effect. So this can be measured directly with the transport measurement, and with performing some scaling analysis, they can extract intrinsic Hall connectivity determined to be 0.14 quantum Hall number, which was consistent with the spectroscopy determined value as 0.13 quantum Hall number. So that, in our understanding, also makes a consistency with, or make a connection to the Barry curvature correspondence. So together we have bulk boundary and Barry curvature correspondence to establish this is an important candidate for the realization of Chen quantum phase. However, there are also problems in this 166 material. There are also because it's a metallic, so it will probably never be exact quantization, and we in future we would need kagome system with cleaner band structures. However, it's an important initial effort, and if we think the stacking of kagome Chen energy gap, this Chen energy gap, we're stacking them along the c-axis. We can think if the c-axis coupling is strong, then along kz direction, there will be certain point that this Chen energy gap will be closing, and that closing point is essentially a well point. So there are also many discussions of magnetic wild state in kagome lattice materials, which mostly are on those materials with stronger interlayer coupling, like a cobalt-tin sulfur system or magnet-tin system, which is the later magnet-tin is a direct stacking of kagome lattice with AB stacking. However, this kind of research are heavily led by the first principle calculations. Usually experimental follow those calculations, and the signature evidence for those fermium, in my view, currently was not very strong. Those are theory-driven research. And on the other hand, the direct electron and wild electron are very fast in the kagome band structure. There can also be very slow electrons, that is flat band electrons in the kagome lattice. There are also many study on this. Initial question was, since those kagome materials are mostly d orbital, from d orbital transition metal elements, So how does this anisotropic d orbital can formulate flat bands? That was initial question, and then people find out if the d orbital, for example, this is the dxz dyz orbital, if they organize in a way that they're in the hexagonal ring, their two polar was facing each other, and then this kinetic energy can still be well quenched and form a perfect flat band. And some similarity to this electronic flat band, people also find that for the vibration mode, if they follow the similar uh, vibration or follow the similar polarity arrangement, the vibration was always along one direction for the hexagonal ring, and then the net force would be zero, means this kind of vibration will be localized and it will form a phonon flat band. And there are some other interesting features because with spin orbital coupling and magnetism polarization, this flat band was always in touch with a parabolic band, and there will also be a chain energy gap opening with spin orbital coupling. And the flat phonon band can couple with itinerant electrons to form this double kink feature. So this kind of electron phonon coupling can lead to density wave order or superconductivity. And lastly, if the system have strong Hubbard-U interaction, and the kagome flat band can mimic the F electron flat band, in that it can lead to some resonance near the Fermi level. This many-body condor-like resonance will be generated. And here I give one interesting example was in cobaltine sulfur, where in its band structure, it has a spin polarized partial flat band. And this flat band was in touch with a parabolic band, similar to the very similar to the tight binding model. And with including spin orbital coupling, one can see there will open a tiny gap. And in the scanning tunneling microscopy, we do observe a strong flat band peak on one type of the surface. And then we use magnetic field as a perturbation to this flat band state. And we find no matter we add positive or negative magnetic field, this flat band was always shift to the positive energy direction. There is some unusual feature. The first feature is if for the common spin polarized states, if we use magnetic field to control it, positive field will shift to one direction, and negative field we would expect it to shift to the other direction. In the current case, it shift to both direction. There was a very simple explanation in that the magnet was flipped by the magnetic field. So this magnetization polarized the effect. Yeah. For example, you have a spin up state, you use up field, and so it will shift to lower energy. And if you do a negative field, and the magnetization of the system is flipped, so it has a lower indeed has a lower curvicity field, has 0.3 Tesla. So this large field will polarize it. So this is a new effect of magnetization polarized Zeeman effect. The other interesting point is that so we would expect it to shift to lower energy. However, it shift to higher energy. It means this means it has a negative magnetization moment. This negative moment can be calculated as negative 3 mu b. So negative 3 mu b was its magnetic moment. So the spin magnetic moment would be positive 1 mu b. So what's the reason for this? This one of the interpretation was come from the orbital magnetism of the chain energy gap. So the first principle calculations and fundamental Kagome model can evaluate, especially the first principle gave the right direction. It is the orbital magnetization direction is indeed the other opposite to the spin magnetization direction. So this was an evidence of negative flat band magnetism in cobaltine sulfur. And later on, what makes kagome popular or as a hot topic was probably due to the discovery of superconductivity in those compounds. There is some superconductivity and is charge density wave order. So this charge density wave order was mostly 2x2 charge density wave order, and charge density wave order density states will open an energy gap, and in momentum space, this was gap was opened on the endpoint, and you can see with pressure or doping, one can tune down the charge density wave order and promote superconductivity. Superconductivity in those material was always around 1 Kelvin, this 1 or 2 Kelvin, not very high. And one interesting feature people now discuss was whether there could be a time reversal symmetry breaking charge order, or whether the charge density wave breaks time reversal symmetry. One of the initial evidence for the time reversal symmetry breaking charge order was in our STM experiment. We see this charge density wave peaks, vector peaks, 2x2 vector peaks, and along 3 directions they have different intensity. And this different intensity, if we count from lower intensity to higher intensity, we can define a right hand or left hand chirality. And this chirality somehow can be manipulated by positive and negative magnetic field. So it couples with the magnetic field, this chirality of the charge density wave. So that leads to some interesting discussion. And then people also found there could be anomalous Hall effect, and μSR also found spontaneous time reversal symmetry breaking just below the charge density wave ordering. And there was also Kerr evidence, and recently there were also chiral transport and torque experimental evidence for that. And of course, there are also many people against such scenario. There are, for example, no loop has been observed in the anomalous contribution to the Hall effect, and many groups claiming they only detect the pneumaticity, means they don't have chirality, they don't see chirality clearly, and there are also discussion whether there could be real Kerr effect in the experiment or not, and those from neutron scattering or spin polarized neutron scattering or other torque experiment, the orbital the mechanism, the time reversal symmetry breaking mechanism was also very tiny, and it's hard to justify whether it's a real signal or not. So this is still an ongoing discussion, and here I mainly want to talk about with our recent progress on the investigation of the magnetic feature of the kagome superconductivity. Initially, this magnetic superconductor of this concept was probably first discussed by Matthias and Anderson when they are when they discover an interesting compound CeRu2. It's essentially a compound with 3-dimensional kagome lattice. So they think that even though magnetism and superconductivity are enemies, but they probably could be married in kagome lattice or some special material. And then we know such magnetism has to be very tiny, and the superconductivity transition is also low. So there is a systematic challenge. How do we measure? How do we detect those tiny mechanisms from the superconducting electronic structure. So that's why here in our lab and SUSTech, we build very low temperature STM down to 30 millikelvin with electronic temperature of 90 millikelvin. And we also try to develop some new methodology to detect time reversal symmetry breaking for group of quasi-particles. So here is a topographic image for those kagome superconductor, for the famous kagome superconductor 135 system. So here's we have imaged all three compounds, and you can see the other two, RBS and CVS, they have some additional stripes, and these 1x4 stripes, although there are different opinions in the field, in our opinion, we tend to believe those are surface stripes because they are not detected by bulk X-ray or neutron scattering. While the 2x2 superlattice both exists in all three compounds, and they are also well detected by bulk X-ray and neutron scattering. So that makes us to focus on the potassium one, KVS. So for KVS, in Princeton, we can detect while this charge density wave gap below 80 Kelvin. And here we further can identify its superconducting gap. It's a U-shaped superconducting gap, but with some large residual density states down to 30 millikelvin. And we can also use superconducting tip, niobium tip, to perform Josephson tunneling. So the zero Bell's peak will be a Josephson tunneling signal, and it is believed to proportional to the Kuiper pair density. So with this high precision measurement, this allows us to measure the superconducting gap as function of distance, spatial rest with similar to the density modulation, because we have 2A density wave order. We want to see how does this density wave order couple with superconductivity, and we determine carefully with high precision measurement. We can measure superconducting gap, coherence peak position has very tiny modulation. We extract the positive gaps and negative gap size, and so we can calculate their total gap size divided by 2. So we can see it has a well-defined 2A modulation, similar to the density wave order. It has an induced 2A pair. This is called in this modern language as a pair density wave, because this modulates the Kuiper pair pairing strength. On the other hand, we also measured Josephson tunneling with a superconducting tip. This Josephson zero Bell's peak signal also modulates as a function of position, and it also has a 2A periodicity, similar to the superconducting gap modulation. So they together establish 2A modulation. So this also measurement also sets up a record of energy resolution down to mu EV level. So let me explain our energy resolution criteria. Do we have a density delta function in our spectroscopy? So we will measure it as a broadened peak with our instrument resolution, 3.5 kBT effective temperature, basically 90 millikelvin effective temperature. And if we have two such delta functions too close to each other, we won't be able to distinguish these two peaks. So we will still see one broad Gaussian peak. However, the measurement for pair density wave situation is different, because we have two energy closely located peaks, but at different position. So now we measure this broadened peak, but if the measurement was accurate enough with high spatial resolution and high signal to noise level, we can still distinguish their difference. So that's the reason why we can achieve such high energy resolution. We all have to combine both three factors: low electronic temperature, high spatial resolution, and high signal to noise level. Uh, so we detected two pair density waves, and now we are measuring it in 2 dimensions. So we measure the pair gap modulation and pair density modulation. In both cases, we see 2x2 modulations. And you can see if we plot these 2x2 vector peaks, um, it always have different intensities. So this suggests the system is pair density wave also can have chirality. And especially we apply positive field and negative field, we can control the chirality. Noting that the chirality is defined with counting the peak intensity from lower to higher. So we can control the chirality. That also indicative of time reversal symmetry breaking of the pair density wave. And we can also see domains. For the upper domain, we see left-hand chirality, and for the lower domain, we see a different chirality. And if we focus on one domain, the chirality can be manipulated with different magnetic field. And we also want to check the chirality for the same domain between charge density wave and pair density wave. And our initial investigation suggests this chirality are opposite with each other. So that is an interesting feature. So in our Ginsburg-Landau analysis, this suggests the coupling, the induced pair density will have some negative coupling constant. And lastly, we want to investigate what's the reason for the large residual density of states. Even though the shape is S-wave-like, but we have a large residual density of states. This seems to be very different from the simple S-wave pairing. So it's the systematic event is a quasi-particle interference within this pairing gap. And below the superheating temperature, especially on the low temperature side, we see the system initially only have a circular feature, and then it become this triangular feature become more prominent. And the system eventually at lowest temperature become the triangular feature also becomes two arc-like feature. So how we understand the emergent triangular signals? Our theory collaborators find out that under a 2x2 band folding or Carroll flux model that was very similar to the Varma's loop current model proposed in cuprates. And we do find those feature of triangles. So this triangle was induced by the Carroll density wave order, Carroll charge order, and then was coupling with a special pair density wave order. Here we consider the supernativity is mainly from the p orbital or the circular orbital, SB p orbital, and coupled with the density wave. So the p orbital provide superconductivity instability, and the d orbital provide the density wave vector. So these two couple with each other. So we have PDW, and then we can have some residual Bogoliubov Fermi states. So the Bogoliubov Fermi states can be consistent with our observations. So this also build up space and momentum connection for the pair density wave states. So we have, in summary, we have Carroll 2x2 pair density wave with time reversal symmetry breaking, and uniform superconductivity occurs mainly in the antimony p orbital, and charge density charge order occurs in the vanadium d orbital, and their interplay produce PD interorbital pair density wave. If we write down their pairing, it's between minus Kp and positive Kd plus Q. That's our understanding of this pairing. So this our tunneling experiment was also inconsistent with the current recent observations with chiral transport. People observe chiral transport, superheating transport with a diode effect and other interesting phenomenon. And angle resolved photo emission also found that it's the inner d orbital that is pairing was very anisotropic that can be consistent with a paradise wave scenario. There are also thermal conductivity or μSR. They found large residual density of states that can be consistently understood within the paradise wave picture. So that our next experimental goal was to design some phase-sensitive evidence for the paradise wave. Initial idea is that the paradise wave, if we use ideal FFLO states, it will have positive sign and negative sign oscillating, very similar to the D-wave pairing in momentum space. So we think non-magnetic impurity would break the paradise wave and provide phase-sensitive evidence. Our theoretical collaborator did some Abrikosov-Gokov calculation for the various PDW, and its behavior with scattering, with non-magnetic scattering, was very similar to that in P-wave and D-wave case. So this could be a probe for the non-magnetic impurity can be a phase-sensitive probe for paradise wave in future. And when we next topic was when we destroy the charge density wave order, and then the paradise wave order was also destroyed. And strangely, we found the superconductivity was promoted, but it is still has some unusual feature that we call it time reversal symmetry breaking. And photo emission and our STM also always find a very well-defined U-shaped gap, fully open gap. This was consistent with photo emission and angle, small angle neutron scattering. People always detect a S-wave gap feature. However, μSR find those pressurized superconductor or this chemical doped superconductor without, in all these four cases, there was no charge order. And when the system entering superconductivity, there was a spontaneous magnetic moment. So that is initial indication of what time reversal symmetry breaking. Then we want to check in which electronic channel the time reversal symmetry was broken. And we again use quasi-particle interference because it has two main pockets. One is hexagonal-like, one is circular-like. So it could have three scattering channels. And we luckily we found the magnetic field tended to this three scattering channel was very sensitive to magnetic field. The magnetic field can enhance the scattering. There's three scattering channels. So we have three scattering channel, and then we want to figure out in which channel time reversal symmetry was breaking. Though the experimental procedure was like we measure the quasi-particle interference, use a positive field, and then we remeasure the same place with quasi-particle interference technique with negative field and do a subtraction of the two signal. And then we found it is the alpha band, inner circular band, that was very special. It has time reversal symmetry breaking signal. And this signal, if we go to energy larger than the end gap, this signal was gone. If we go to magnetic field higher than its upper critical field, this signal is gone. And if we go to higher temperature than its critical transition temperature, this signal is gone. So this time reversal symmetry breaking signal is intimately related with superconductivity. But the problem is for the μSR technique, it was measured with a zero magnetic field, and here we are measuring with finite magnetic field for the time reversal symmetrical quasi-particle interference experiment. So we want to have a separate experimental to build a connection. So lastly, again, we check the energy gap modulation and the zero field. And again, we do detect there was an abnormal signal and the same Q alpha, the alpha band. Alpha band has the gap modulates, spontaneous modulates an alpha band. But what was the mechanism for the gap modulations? It turned out to be a parabraking scattering mechanism. Uh, we found this in the Luyu's paper, what was a very famous Yushiba YSR state paper. In the initial white paper, in his supplementary, he derived this equation for magnetic impurity near for S-wave superconductor. So the autoparameter will oscillate and KF. And then Donghai Li recently extend Yu's theory to other two cases. One of the cases is relevant to our case is that the non-magnetic impurity effect in time reversal symmetry breaking superconductor will also have such oscillations. So together we have three evidence for the time reversal symmetry breaking nature. One is the mu-SR evidence detected at zero field. It was a spontaneous mechanism, and then we have quasi-particle interference signal, symmetric quasi-particle interference, and Q alpha. And we also have spontaneous pair modulations and Q alpha, also at a zero field. So this built an evidence chain. So each of the two was connected to reveal the time reversal symmetry breaking feature. But what's the specialty of alpha band? And from the first principle calculation, we found in the doped case, the alpha band both have PZ orbital of antimony and DXZ, DYZ orbital of vanadium. So there's some mixed orbital. Was probably the DP orbital hybridization could be important, but we still don't know the exact order parameter. But apparently it was consistent with the proposal by Xiaogang Wen was proposed with some PGIP or P plus IP or other Jia-Xin Yin proposed D plus ID, the initial theoretical paper. So our proposal was there could be some delta 1 plus I delta 2, but we still don't know the exact order parameter. Note that even in strontium rusinate and iridium ditelluride, it's also open question. So our current, this is summarize our current understanding for the magnetic kagome superconductivity or the magnetic feature of the kagome superconductivity. For the charge order, it have a 2x2 chiral charge order from d orbital, and it breaks time reversal symmetry. And in the Sylvanian state, this S-wave superconductivity mainly from p orbital, and it couples with this d orbital charge order to produce a 2x2 pair-density wave. And if we destroy these two phases, and we are left with still an unusual pairing state, was probably D plus ID or P plus IP pairing with a mixed D and P orbitals. And if we look at the scaling, the Umura plot, the superfluid density versus TC, this material was also not very conventional and not very strongly correlated. It's actually in between. This is the cuprates, and this is a conventional superconductor, BCS superconductor. It's actually in between. So it was the most challenging part was in-between case. We don't have a well-defined theory for the in-between case. And lastly, I would like to talk about some opportunities in spin liquid. We just started this chapter, and we initially we did not go directly to spin liquid. We studied a metallic spin ice, kagome spin ice compound. This material have a spin ice ground state. And spin ice means in each of these triangles, the spin are either in a 2 in, 1 out, or 2 out, 1 in configuration. And in our STM study, we tend to find two giant inelastic tunneling signals. These signals was probably we speculated could be due to some spin flip in elastic tunneling. but its energy was too large, was 100 millivolts. And in this system, the spin exchange interaction was very small, was only on the order of 1 millivolts or 2 millivolts. So how do we have 100 millivolts energy scale? So we propose to use some model, use a two-step model, because the system was a spin orbit coupled system. Then if we want to flip the spin, we need to flip the orbital together. And the intermediate case of orbital flipped case, it has very large energy cost. So that was the reason why we see this resonance states at very high energy. And the bring home message is that the local electric field can have some control over the spin liquid magnetism, but it requires to climb over the spin orbital coupling energy. So that is useful for our future application of this spin liquid material to electric devices. And our ultimate question for this direction for electronic research methodology is how do we characterize the long-range quantum entanglement with our technique? That is still a puzzle in the field. And lastly, I would like to comment on the overall challenges in this fast developing field. There was many that come back to the topic, quantum diversity or quantum party, even we call it, in the kagome lattice. There are many different fancy words, fancy discoveries in those fields from many different groups. But in my view, including ours, they all fall to two categories. Either they are about superconductivity, or they are about the quantum Hall physics. That is also our challenges in condensed matter physics. It seems that we currently only have these two macroscopic quantum effect, and whether through hybridization of multiple interactions, especially in the kagome lattice, there are so many exotic interactions. Whether combining those interactions, whether we can find the third kind of macroscopic quantum phenomenon is our I take it as our responsibility and for our generation. Okay, thank you.